Today, you're going to get an up-and-close look at all the different mechanisms of one of the most competitive catapult robots that I've seen this season for the FTC Decode.
These ranking points becoming increasingly valuable towards the front of the field. No, actually, they catapult that way. So that artifact does...
I'm Coach Pratt, and I'm teaching robotics and design for over a decade now. And I've led FTC teams to winning national championships. And today, I sat down with team Born to Build 31065 to talk about their awesome catapult design. Now, their robot didn't make it through the next round, but it doesn't mean that the design isn't still a really useful piece of tech to be able to learn something from. It's got a 3-piece catapult with an interesting string winding mechanism, and it's got a really quick and clever intake to be able to pick balls up, launch them into those 3 balls, and have some way of channeling them across the system as well. It's certainly a team you can learn some design mechanisms from. So tell me about your general strategy to the season. What was your approach?
So at the beginning of the kickoff, we want to have a robot that was capable of anywhere on the field, because especially in the far launch zone, if you could cycle between the human player zones and the far launch zone, you can have a really efficient cycle time.
Yeah, and we didn't really know exactly how we're going to approach stuff, so we wanted to do a modular strategy where we could kind of build different parts of the robot individually. So we didn't actually know we were going to put catapults on this robot at first. We knew that we wanted intake that was really big. Started with that part, and we kind of planned out the robot for whatever we're going to put here. We didn't exactly know that. So then we kind of did some tests with a shooter prototype and a catapult prototype.
Tell me about how you actually go about picking things up off the floor.
We don't really have a way to slow down. We have like a slow mode here and then a fast mode. So did you get what it looks like?
Wow. Yeah, that's pretty quick.
All right.
Cool. That's actually pretty efficient at being able to index it into those catapults as well. Now, those white wheels look really interesting. Can you tell me about those? Are those like custom cast wheels? Are they TPU 3D printed? What's the deal there?
Those are custom molded silicone wheels. We created like molds to pour 2-part silicone into it, and then we had cracked the mold open with a bunch of hammers and then cut them slightly to make them smaller, and then we install them on here. And they're really efficient because they have really great geometry while having the very tacky material properties of silicone.
Mm-hmm. Do you happen to know the shore hardness you guys use for that pourable silicone? I'm assuming you use like a 3D printed mold, poured a bit of mold release or sprayed in mold release, and then poured in your 2-part silicone.
Yeah, it is 30A silicone, I think.
Well, okay, so pretty soft stuff then. And that little bit squishiness helps it get up. And you've got what looks like masking tape on the front wall there. Is that actually masking tape on the wall that it pushes up against, or what else is on there?
There's stuff that's like really grippy material that helps the balls roll up the ramp. Without it, sometimes it'll like kind of like slide backwards and then we'll right up easily. So that thing really helps it get up.
Is it kind of like grip tape, like a skateboard grip tape?
Yeah, it is.
Yeah.
Cool. Awesome. I love using non-standard robotics parts in it. And you got a couple compliant wheels, and then it looks like you have, are those large PLA printed boot kickers up at the top, or what are those really thin lime green?
With TPU. I like TPU forkies because we made a bunch of them. They weren't so functional at the bottom, but they work pretty well up here for getting it to continue through a pretty far distance away from the balls.
Mm-hmm. Cool. And yeah, I mean, that thing is surprisingly efficient at being able to pick the artifacts up and get them into your catapult. Now, you had a slow mode and a fast mode. What's the purpose of slow mode?
Well, we got some, a lot of penalties and cards for accidentally picking up too many. So the main thing there is like the drivers got better at it and got more time to practice, kind of going in a way that they could actually see what they're picking up instead of blindly doing it. But another thing we tried is a slow mode, which is if for whatever reason we have to go at a really big clump of balls and they're not going to be able to go at it in a way that's going to, you'll see that's okay. They're not going to be able to go at it in a way that's going to be able to like control how many are going to go in. So they can use a slow mode. As you can see, it's stalling out here. Like it can't pick up anymore. If you have 3 here, it works because you just can't pick up anymore. And then start backing away, they can go back and the rest will go in.
Okay, so slow mode, you almost just deliver like not enough power to the motor. It allows you to get just a few in, and then you can drive away and start giving her.
So in the case that we're picking up more balls on one side of the road, that didn't work as planned. But if it goes here, then we pick up another one, and we can't do that. We have to use our little cutting arms here to get it into the other.
Okay.
So that's kind of our solution there.
That works great. Yeah, it's just a little angled piece that comes out. Is that a manual solution? Do you just hit like one of the triggers to be able to move that over?
It's joystick on the operator.
Yeah.
Okay. Very cool. Cool. So once they're there, how does your catapult mechanism work?
Basically, how the catapults come back is there's a string here. And that's good. So maybe you can get in here. Right there. So there's a string here for the right one, and a string here. And you can see there's a little bit of tensioning springs on there just to make sure they don't come off the pulley like they did in our first few competitions. And there's pulleys here, and they're all connected to one axle. And then there's another axle over here, which is for basically extra keeping them, another thing to keep them aligned and mostly just to keep the gears aligned. But that's our extra axle to connect the two motors side to. So our gear thing, we'll just keep on pulling these back using these 3 pulleys. So when it's doing that, it pulls them back all at once.
So it comes back, and then there are these hooks that hook onto these protrusions on the catapult. It's like this thing comes back and hooks onto
like a little hook.
So there's the servo arm, and that is the part that pivots up and over. Okay, and that is what holds on to the mechanism. And then does your gear de-wind at that point then?
So get the catapult back, we hook it on, and then it's good. So here's our gears over here, so you can see it. We got so this is going to the main axle, and this is the secondary axle through there.
Yep.
We help with those. So at that point, so we can unwind however much we want to fire. So if we unwind all the way, that's fire zone. And then we just have a hard stop here, which hits when we let go. And then show you basically, this is a full power shot. Maybe that's not quite full power because we had to widen it up a little bit. But the cool thing is we don't have to always do that. We made our strings really strong because we really wanted to be able to fire from close zone too. So if we, let's say, only unwind halfway, that's only going to catapults rotate like halfway-ish, and it's not fire with its full power. It's going to go in a more upward, but it's also going to be able to get in from the close. So we have an equation for how much we unwind based on the distance to the goal, which is calculated by the sensor on the bottom of our robot.
Cool. Is you're using a distance sensor to figure out how far you need to go?
No.
We're using the SparkFun OTOS sensor.
Okay. Yep. So using that as a like an absolute positioning system for knowing where you are.
Yeah.
Cool. Okay. And then you also have a camera on the top there. You're using that to help auto rotate your robot towards the goal. Is that the idea?
Yeah. Now we have that. We've gotten that working for only the last competition. Mostly like the OTOS, we use that because like we know the X and Y distances. So from that, we can use the Pythagorean theorem to figure out what the hypotenuse is, like the diagonal distance to our position, whatever it is. And that's our distance in inches. So that's how we figure out the power. And then we used to also use aiming for that by calculating the angles based on the size and stuff. And that worked okay, but the drift over time. So then we got this camera up here, which does, I think it's typical April aiming. We were trying some more complicated stuff, and that wasn't really working. So,
and then for indexing, do you have you've got 3 lights that are kicking down onto your catapults. Are those color sensors, or is it a manual based index?
Well, these are color sensors, and we only use them in auto because in teleapp you don't need. It's like if a lot of times in teleapp stuff goes wrong with the pattern, you kind of have to fix it. So our robot's really good at that because you can just fire whichever one. So if another team has like 2 greens or something, we're fine. We can put in purples or greens or whatever needs fired, as long as we can think it through as a drive team. We do automatic distancing, so that's like auto powering. We have auto pullback, so if they fire all 3, it's going to come back immediately. We have auto aiming, and we have a slow mode. I think that's it. They do the arms on their own. They run the intake on their. There's another button to pull back any catapults that haven't been fired yet. So or have been fired. So if you have one back already, it knows that you haven't clicked the button to fire it yet. So then if you press to pull back any remaining catapults, it won't pull back that one. Only the other ones are going to open and come back. So you don't want to accidentally fire when you're not launch them.
Yeah, you definitely wouldn't launch into a referee or somebody in the audience, right?
Right. Yeah.
Very slick. So what are you most proud of about on this robot?
Probably the catapults. It's been a very long journey to get here. Previously, we have a ton of problems with the string breaking, both due to the string itself and how we anchor the string. So that's something that I would say is very hard for us and the gears as well, because these catapults need more than 100 pounds of force to bring back. So a ton put into this to make this as robust as possible. And that's what I'm very proud of.
Yeah, it's really cool to see a catapult that's pretty competitive as well, because I think a lot of teams have run with flywheel shooters, and it's really cool to see some of the engineering that's gone into this, having different mechanisms, having different touch sensors, different ways, using a lot of creative materials like rolled up sections of duct tape, using touch sensors in a way so you know when individual sections are there, using skateboard tape. I love seeing non-traditional robotics parts being used in robotics parts. That's really slick.
Thank you.
Yeah.
Well, thanks for sharing your robot, guys, and best of luck out there this season.
Thank you.